Lab 2 follows the same experiment as Lab 1. Two pieces of tape are charged and used to repel each other. However, the key difference in this lab is that the tape is no longer treated as a point charge. Instead, the two pieces of tape are modeled as line charges, with the same amount of charge evenly distributed along the length of the tape. In the next few minutes, I'll be discussing the experiment itself and the key principles involved, the model used, and finally the method used to determine the charge. The setup is as shown in the image here. The two ends of tape B are attached to two books, and tape A is used to repel tape B. With tape B motionless but still being repelled by a charged tape A, two fundamental principles can be identified here: Coulomb's law and Newton's second law. Electric force is most definitely present as tape B has moved away from its original position from tape A. Because tape B is motionless, its momentum and as a result net force are zero. To find the charge on the U-tapes, the U-tapes were tested in three scenarios: with each other, with a negatively charged pen, and a neutral book. They repelled each other, were attracted to the negative pen, and were also attracted to the neutral book. Thus, the U-tapes were determined to be positively charged. The new charge that was found in this lab was 2.5775 times 10 to the negative 8 coulombs. The observed data found the length of tape B to be 0.199 meters and the separation distance to be 0.025 meters. The calculated data found the mass of tape B to be 0.000199 kilograms. A sample calculation can be referred to on the right-hand side. This model was developed under two assumptions. Air resistance was negligible, and each U-tape was a long rod with the same amount of charge distributed along its length. In this model, the line of red spheres represents tape B, and the line of blue spheres represents tape A. Each has 9 spheres, which represent the 9 point charges both were split into. The green arrows represent the electric field arrows coming from the multiple observation points of tape B. Finally, the large white arrow represents the electric force arrow, which is equal and opposite to the yellow arrow on the bottom. The charge of 2.5775 times 10 to the negative 8 coulombs was determined through the guess and check method, where multiple numbers, each getting closer to the final answer, were input into the code until the magnitudes of electric force and gravitational force were within 3 decimals of each other. The following code represents the model of the system included in the previous slide. The first section includes the physical constants, with the first representing Coulomb's constant and the second representing the gravitational constant. The next section contains the observed values, with the first representing the mass of one tape in kilograms, the second representing the separation distance in meters, and the third representing the net estimated charge on one piece of tape in coulombs. This was determined through the guess and check method. This part includes the function for electric field and will be called on in the for loops we'll see later in the code. This section of code contains a function which creates a line of charges. It's called on in this section with the output top tape and bottom tape to create the line of red and blue spheres, which model the collection of point charges along the length of each piece of tape. These for loops below are used to calculate and model the electric fields along tape B, and essentially have the same purpose as a double integral. It also calculates the net electric force on tape B. The final section of code creates the electric force and gravitational force arrow, which are equal and opposite in direction. So how do the previous lab's model of a point charge and this lab's model of a line charge compare? The point charge value is less than the line charge value, because it doesn't consider the other charges on the two tapes that could be acting on each other and contributing to the overall fields and forces. Thus, the line charge would be closer to the actual value because it holds up to a more accurate representation of the real-world system by including these additional charges.